Hello and welcome, folks. Today I'll be explaining a quite interesting problem. You're going to enjoy it. The solution, you're going to really enjoy that. Now, let's derive and demonstrate this statement. So basically in this statement, it says that you're going to be given an n-length array, okay, and that length should be at least 2. What you have to do, or the allowing operation that you can do, is that any adjacent 2 elements, you will turn them, you have the ability to turn them into one element by resulting as the XOR operations of those 2 adjacent elements. And you can follow these operations, but you have to output an array where each and every element is equal. Also, another condition is added that the final element is going to be have to be at least 2. So at least 2 length element of array you have to create at the end of the day, where each and every element should be equal. And the allowing operation is that every adjacent element, you have an option, or you have a possibility that you can do that operation to replace those 2 adjacent elements with its XOR value, and then the array shrinks down to a lower size, but it cannot be shrinked down to one length element, one length of array. I hope you get that, why it's not, because we have to create an element, create an array consisting of at least 2 elements where every element is equal. Okay, I hope you get a clear-cut explanation of all of that. Now, let's take one example from the test set here. Now, let's say we're given 3 elements here. How is the answer yes here? If I do a shrinking operation here for these 2 adjacent elements, it boils down to, it shrinks to what, 0 and 2. If you do an XOR operation, it's gonna become 2 and 2. So if you could see that 2 elements are equal, so you have to find some way, somehow, to make it possible. Also, one thing to notice, if you look at the constraint here, you would see that n is not more than 2000, which means there is a possibility you could do some kind of n² solution, or maybe some kind of brute force. It might happen. Okay, we'll dive into, there's a much more optimal solution than the n² too. I'll also talk about that. But before diving into the main part, or the main solution, I have to derive one thing, which is, we know that XOR value has a pretty cool observation here. It has a quite interesting characteristics, the XOR value. What is that? Let's talk about that here. Let's say let's say a is a value or variable, and I do XOR operations with x, another variable, and the final output is p. If this is what we can call a statement, that the 2 values XOR is going to give us the sum answer, then I can also say a XOR p can also give me x, okay, x XOR p can also give me a, okay. Thus it moves forward and forward. All possible combinations, I can make it happen. It's possible always, because it is the XOR operation. If you look at the properties of that XOR operations, you would see that only when 1 and 1 gets XOR, it gets 0. Apart from that, everything is just like the OR operations. And this is the main part where 1 and 1, if you do 2 binary number, let's say 1 and 1, XOR it gives us an output as false, which is true. Output as false, which is 0. So that derives us, or that drives us to make that property. So XOR has this beautiful property here. We could make it make our strong move for that. How we can make it, which is, let's say we could actually find out some particular subarrays XOR values with that. How is that possible? Let's say I want to find out, let's say this is an array A, and I want to find out from ith element till the jth element this value's XOR properties. I want to find out that somehow. How is this going to help us? I know I don't now for finding out this value, okay, this subarray's XOR value, I don't need to run a loop of n square and try to find this subarray to make an resulting value as the XOR value of this subarray. I don't need to do that. Instead, I could do it in big of N. How it's possible? Right, I told you that XOR has a property. With the help of that property, I can make it happen. How? What we will do is we're gonna create a prefix of XOR operation. Okay, prefix. So I would say that this J, I would say that this is my prefix of J, which means from the first element of this array till the jth element, if you do an XOR operation, it will give us a value which is pj. Let's assume it's pj, it's pj, okay, and the same type of value, which is the prefix or cumulative XOR operation from the first index till the ith index, which is p of I. Now if I do an XOR operation here, just imagine, what should it give me? I'm doing an XOR operation, this with the whole prefix till j. What should it give me? What it should give me is that, just imagine, just think about it, this property gets common to all of these two prefixes. So I told you, if they get common, if the order gets common, what it gives? 0. If you do XOR operation of 0 with 0, it gives us 0. If you do XOR operation with 1, it gives us 0, which means nothing is left here. No binary positive or true value left remain. So the common part gets boiled down to nothing but 0. I hope you get that. And with this XOR operation of P of I and P of J, what I get the XOR operations of P of ij. What does that refer? That refers that from the ith index till the jth index, I can find the XOR operation by allowing the operation to continue, which is P of I XOR with P of J. I hope you get that. That's a very nice observation, which is going to help us to solve the following problem that we were talking about. Okay, now let's dive into the main solution here. What we actually have to do, we have to actually find out the array consisting of at least 2 elements, where each and every element have to be equal. Let's imagine that array now. I have each and every element like this, and let's say x, I have somehow, if you look this problem from the different direction, you will have quite a clear time here. You will understand that problem a bit more if you think from the last to the first. Okay, let's assume that somehow we have made the whole array as an element, allowing those adjacent operations, blah blah blah. We have made somehow an array final, which does consist somehow. Okay, I don't know how I did that, but somehow there's a operation. I have found out that, okay, this is my final array. I have figured out that it is possible where each and every element is the same. Okay, 1 2 3 4 5 6 7. Okay, let's dive into 1 2 3 4 5 6. Okay, so for 2 conditions, I'm gonna talk about 2 different situations that might occur. Now what actually is happening here. If you could have a closer observation, let's dive in for when n is equal to or when, okay, not like that, okay, look what actually this particular value is defining. I could even say that this particular value is actually defining that some subarray from this array, as the operation is only allowed in adjacent directions. So I could say this value, okay, each and every element of our final array, where each and every element is basically the same, is actually, what is actually it referring? It actually refers that this value that we found out, let's assume for this element, this is this value comes or boils down from some subarray which actually shrinked down to that. So some subarray shrinked down to this value and became this value, which is nothing but x. Similar case goes to that, similar case goes to that, each and every element x. So each and every element x is actually referring some subarray from L till R, I could say, from L1 till R1, I could say, okay? So they somehow boil down, I could say that, okay? I could have an observation that and say that, okay, L1 to R1, they boiled and shrink down, allowing the operation that we had to do, and shrink down to only one element, which is x, and it is giving us a positive result because each and every element is nothing but the same. I could somehow make that, okay? That's cool. Okay, now interesting observation is when the same element x is actually even times, let's say even times, they're even to 1, 2, 3, 4, 5, 6, okay, I've figured out even times of elements where each and every elements are same. I don't need to do any kind of operations to verify that. I just only need to do one thing, which is XOR the whole array. If I XOR the whole array, and if now think this array as our temporary array or final array, you could say that. Think about this final array as our final array, okay? So if we do all of XOR operations, what actually it gives, you will always see that, okay, there are always even number of x. So we know that even number of possible solutions, they get XORed out to 0 always. If you do 5 XOR 5, it will definitely give you 0. I hope you get that, what I'm trying to make you understand. Because there is even number of elements of same value, so it doesn't matter what operation I do, at the end of the day the result will be 0. So this is one case where this property might occur. So I hope you get that. So so one way to verify this is that if you initially, when you take those values, okay, of the array, you just do a prefix prefix XOR operation, and you would say that if the XOR operation of all the element is 0, then the answer is yes. Otherwise you are sure that there is gonna be even number of same elements, no matter how much I manipulate those values to make it. Even number of odd number, sorry for that, odd number of same elements there will definitely and always be when this operation does not happen. So I hope you get that for the even part. If these sort of values comes even number of times, then it would definitely allow us to assure or verify that if we don't have to do anything apart from just XORing the whole array. If it gets 0, then the answer is yes. Otherwise, if it's not, then you are definitely sure that there's going to be some amount of elements who are equal, and that element's number is actually odd. So you will always have odd number of final array elements, like 3, could be 5, could be 6, could be 7, Okay, I hope you get that. How to deal with those things, that is where it goes to the main section of the part. Now imagine I have manipulated the array, and I have found out that 1 2 3 4 5 6 7. Okay, somehow I have found out that, okay, this is my array where I have odd number of elements who are equal. Now you don't have to go for all of these values, okay? What you will deal with is only sections of 2 elements or 3 elements. Why is that? For sections of 2 elements, I already discussed that, which is if the elements are odd. At the final array, if the elements are odd, that's what the case of 2 pieces occurs. What about the 3 cases or 3 pieces, which is this? It doesn't matter how much of odd number it is, you can always make it to 3 pieces. How is that? Now look, 1 2 3 4 5 6 7. There are 7 number of elements which are odd. Now if you do an XOR operation of this 2, it will give us 0, nothing but 0, or it will boil down to, okay, and it will boil down to 0. And if you do an XOR operation of 0 with x, it will give us x. And if you do an XOR operations with this x, it boils down to 0. Okay, now if you do another XOR operations with this x, it gives us nothing but x. So ultimately what actually remains is a piece of 3 cakes who have equal flavor, which is actually telling that they are equal values of parts. So you only care about 3 part of the array or 2 part of the array. For 2 part of the array, we've dealt with that. And for the odd part of the array, we know we have to only consider the 3 part. Now, what I told you initially is that what does this x actually refers? This x actually refers to some subarray of the original one. This also refers to some subarray of the original one. This does also refer to some subarray of the original one. I hope you get that. So what you have to do is simply go for all the possible 3-way of subarrays that you can create and make their XOR and check if their XOR is equal or not. If they're equal, then you have got your answer. It's going to be yes. Otherwise, if it's not possible, absolutely the answer is no. I hope you get that. So this is the big of n squared solution part. Okay, now let me derive you to the what do we say, the solution for, oh my god, look at that, it's lagging like, okay, so what we were talking about is checking out the big of n squared solution here. So let's check it out. What actually we told you that, I've told you that we're only considering for the 3 parts of the array. So each and every 3 part, I'm going to be just checking the XOR operations of the 3 part. Now look, taking the value n and then taking the value ai, each and every element. This is the prefix dealing with the prefixes, each and every prefix. Okay, I'm dealing with as a dp portion. If the dp of n equal 0, which is actually nothing but referring the XOR values of each and every element. If it's 0, then the answer is yes. Otherwise, if I deal with otherwise I know I have to deal with 3 parts of the array. So if I have to deal with the 3 parts of the array, how do I do that? Remember what I told you, the property for the XOR value, which is this, that I've already told you, which is actually happening this inside this now if you take a closer look, each and every subarray that I'm taking, for each and every subarray, I'm actually considering, let's show you here, I guess. what I'm trying to consider is this is my I and this is my J. What I'm trying to find out is this is XOR, this XOR, and this XOR gets equal or not. I'm just trying to find out this inside this loop. Okay, now what is this temp referring? It's dp of I times dp of j, not times, it's actually XOR dp of j. So dp of I is referring to this and dp of j is referring to this, which means the allowing operations is this. Okay, so I'm trying to find out this dp of I XOR dp of j giving me this, so temp gives us this. I'm checking if temp is equal to this first prefix right there, and also checking whether if they are equal, and also this value is equal to all of these two or not. Just by doing that, I hope you get that. That's exactly what TT means, dp of n XOR times with dp of j, which is nothing but, let's say this is n and this is j. If I do XOR, I get this part. Now I've got all of it now. Okay, so finally just taking out, looping out if the flag value is equal to 1, and then the answer is yes, otherwise the answer is no. So this was the big of n squared part. What about the big of n solution? I have an n, so I just actually got to realize from the editorial portion that there is a big of n solutions. I looked at those solutions, so I'll just talk about that here right now. So what I told you, what do I actually have to deal with at the end of the day? I only have to deal with odd number of groups where each of those elements are equal. Okay, let's say this is the odd number of groups. Okay, 1 2 3 4 5. Okay, now what is these each and every value is actually referring to? It is nothing but referring to some XOR operation, nothing but the XOR operations of those subarray. I could tell that this X is actually nothing but referring the XOR operations of the LR subarray. Alternatively, this could also mean something like that. It's the nothing but the XOR operations. What you actually generally do is the XOR to make it shrink it, boil down to this. I hope you get that. Okay, so 1 2 3 4 5. So I've got odd number of groups. Now how do I know that I get if I could somehow make it happen that I have odd number of groups of this value as my subarray element, odd number of groups of XOR value as X, which that odd number should definitely be greater than 1. Okay, greater than X. If I could somehow deal with that, I know that the answer is always yes, because I know for this I can always get that, right? I can always this does refer to the final array. So how do I get, or how do I measure that I have at least at least two of those odd groups where each and every where the XOR value is the same as X? How do I deal with that? Now if you could generalize, if we could see that no matter what odd number of X or no matter what odd number of equal values are there, if you do whole XOR of the following array, the initial array, you will get a number X always. What was that X? That X was these members. It's obvious. Let's take a look at it. If you do X and X XOR, then it gives 0, and if you do 0 and XOR with X, it gives us X. That's all we care about. That's all we care about. It gives us X. So I hope you get that. Any kind of odd number of XOR values, it gives us that value itself, equal values. That gives us that value itself. I hope you get that. So I know that my final array's result is actually the whole XOR of all the elements. So I have that in my hand initially when I did those full elements XOR. Now if I do have that X, and let's take a look at it. If I do have that X as my resulting Now, what do I actually care about? Just imagine I have now, just imagine you don't have to go for the final array, you only will go for the initial array. You will run out a big of n loop, for loop, L1 till R1, I say, if L2 till R2, should I say, blah blah blah. Okay, so after finding out that x, that x is definitely what? The final arrays, if you could somehow make that the final arrays, the value that is left. Okay, I hope you get that. Okay, this part. Now, what is this? How is this res or total? This is the total XOR value of all the operations of all the elements of the initial array. I hope you get that. Now, how is this going to help us? For this res of x, I know that, yes, I have found out my tricky part. I have found out my team team members element, where each and every element are same. Now, what I only have to care about is just do XOR. Okay, now if you do XOR, you will know that you will do XOR, but starting with another value. Let's say you have a temp. You will be trying to do the same thing as you did before, trying to find out the prefix XOR. So that prefix XOR goes down, goes here, and he does XOR this till from L1 till R1. When it comes to R1, you will see that this temp is giving nothing but X. Okay, because it has to give, because I've already told you that this X refers to some subarray, so always it's going to give some X. So inside those for loop, you will check whether temp is equal to my result or not. This temp is equal to my result or not, which is, what was our result? Our result was X, and I'm comparing it with X. So I'm comparing X with X. When I do that, I will know that yes, I have in one subarray which does shrink it down to X. And when I do that, I will simply initialize my temp value as 0. Why? Because I've already found out one subarray of small subarray which does shrink down to X. I don't need to deal with it. What I only will do is initialize that value with 0 and count the number of groups of X. I hope you get that. When I found out count the number of groups, I said now the temp is 0. When the temp is 0, and then when it starts from this loop, the temp is 0. But when it's 0 and it goes to till a of R2, it gives the same value, of course, which is X. Then you will know that, okay, I've got another group, and I will do the same thing again and again and again. Ultimately, I will check how many groups I did have. You will check whether that group number is greater than or equal to 3. If it's greater than or equal to 3, yes, I've got my answer. Because you know why greater than or equal to 3? Of course, it does have to give even odd number of solutions. It will be either 3 or 5 or 7, doesn't matter, does it? No, it doesn't matter. Greater than or equal to 3, always got my answer, and that is where I terminate my process of execution. And this is the code for the optimal one, just doing the XOR and checking out the same thing. It's pretty easy. I hope you get that. Then checking out the group numbers. If it's greater than or equal to 3, then the output is yes, otherwise it definitely has to be no. So I hope you clearly understood the problem, and yeah, so till next time, goodbye folks.